thank the organizer for the invitation. I'm very happy to visit this very beautiful city. I will also talk about the Blasius conjecture. Yesterday's talk of Siyu. I will first talk on general setup. Then I will give 3 examples on Rankin-Selberg L functions and Hickel L functions. You know the Deligne conjecture for K E be number field. K is the base field and E is a coefficient field. And for every pure motive M, Deligne's conjecture, which is extended by Blasius to a general coefficient system, assert that is the critical value of the motive, L value of the motive, divides the period belonging to E. For example, we know the rationality limit zeta function is due to Euler. And another example is the famous BSD conjecture, which asserts that the value at 1, L value at 1 of an elliptic curve of a Q is rational up to this integral. Yeah, omega is a rational one form. In this talk, I will concentrate on the automorphic version of the Deligne conjecture. This is due to Blasius. Let pi be an irreducible cuspidal automorphic representation. We suppose that pi is algebraic, is defined by Clausius. Then the value of this L function of pi at a critical point is belong to the number field of definition of pi after dividing some automorphic period. We studied the rationality through auto C equivalence. This is called the reciprocity law. Here is general setup. So G is a connected reductive algebraic group defined over a number field K. And suppose we have an index set called I, which we equip it with the discrete topology, and assume we are given an auto C extreme or this index set, which factors through this alpha group. Assuming this extreme is continuous, then the fixed point of every stabilizer in C is a number field. This E is a number field. Okay. To study regular algebraic automorphic representation, we need some coefficient system. This is coefficient system for cohomology. So we suppose we have a equivalent bundle over this discrete set I of irreducible algebraic representation of this complex group. Okay. The coefficient system is a bundle over this index set with an extreme of this group. Okay. Yeah, each Fi is irreducible algebraic is a representation of this complex group. Okay. And for each sigma in auto C, which maps I to J, the map from Fi to Fj should be sigma linear. Okay. Doesn't matter, just a discrete set. Yeah, just a set with discrete topology. Okay. And we also need to assume this auto C I, this stabilizer group, all vectors in this Fi fixed by this stable group is an EI form of Fi. So this is a continuity of the Galois action. Let's give an example. For example, we assume G is quasi-split and U is a maximal unipotent. And let I be the set of all isomorphism class of irreducible algebraic representation of this complex group. Then we can consider all algebraic functions on this quotient space. And this space carries a natural action of this semi-directed product. And when restricted to this complex group, the representation, this space is just direct sum over all irreducible algebraic representations. Okay. Then this action induces an action of auto C on this I, and also we have such an equivalent bundle. Yeah, the action is just induced by this action. This is our coefficient system. Yeah, in later examples, I will only use this example, or some coefficient system induced by this one. So we have the real arithmetic manifold. We have xg. Here K infinity is more or less a maximum compressible group. So we also put the connected identity connect component of this largest central points of this largest central sphere torus in this group, restriction of K to Q. We use this circle to indicate the identity connect component, and we use this sharp to indicate the group of all connected components. Then this group, this is a totally disconnected group. This group has natural action on this arithmetic manifold. And for each I, we can consider the cohomology space with coefficients in this Fi, the dual of Fi. And we put all these together, and this space carries a natural action of this group. Yeah, this phi indicates a certain support condition. For example, we can consider cohomology with compare support or arbitrary support. And this Fi check is the dual of Fi. So put all these together, this is also a bundle over the equivalent bundle for this group. KF runs over all open compressible groups of this non-Archimedean group. This is beta cohomology. And for non-Archimedean group representation, we also assume we also have such an equivalent bundle. We assume we have a family of a bundle of representations of this group. Okay. We assume is a representation of GAF. This guy is a smooth admissible representation. May or may not be irreducible. Okay. And for each sigma that in auto C that maps I to J, we assume this map should be sigma linear. Okay. And similar to the coefficient system case, this fixed vectors of this group in this non-Archimedean group representation should be an EI form. This is also a condition on continuity of the Galois action. We fix an additive character psi of A mod K. This we just fix this real one. First, take a trace to Q, and this take a projection to this guy. This is equal to R mod Z. And this is a real exponential map. Okay. Let me give you an example of this guy. This is this example is due to harder in J2 case in the Minkoff in general. We consider this U is just usual maximum unipotent group, upper triangular unipotent group, and on this group we have a character induced by psi. Okay? This is a usual character, and then we can consider the smooth induction. This is smooth representation of this finite Dell group of this GAF. Okay? And this space carries a natural action of this product. This, of course, this non-Archimedean group acts by Reuter translation, and this guy, the action of this guy is more subtle. This is given by atomic character. We have the map from auto C to by restriction. You get this guy. This is T sigma. This element is called T sigma. Then the action of sigma on phi is given by this formula. Here we induce from a unipotent group.
Is it normalized by
this is unimodular. Both group. Yeah. These are
it's from you, I'm sorry.
yeah. They are unimodular, so they are the same.
Sorry.
This is action of the auto C on the space of all these vector functions. And let I be the set of all isomorphism classes of generic, reducible, admissible smooth representation of GAF that are definable over number fields. Then use this vector model, we get an action of auto C times this non-Archimedean group on all these destroying unions. We get an equivalent bundle. Okay. Here, for each, I is an isomorphic class of such a representation, then we can consider this as a representation inside this space. Multiple one, okay, with a model. This already mentioned that this example is due to harder in the main course. Another example, we consider P to be the stabilizer of a hyperplane in Kn. Okay. This is a maximum parabolic of G, and this group has a natural action on GL1. GL1 is identified with a general group, a general linear group attached to the quotient space, the quotient of Kn by this hyperplane. Let I be the set of all smooth characters of this AF cross, whose image is contained in number field. Okay. Consider all such characters, and then attached to I, we define such an unnormalized induced representation. KF is viewed as here should be AF, this should be PAF. KF is viewed as a character of PAF through this homomorphism. Okay. Then we also have a bundle of non-Archimedean representations that there is auto C action. This is unnormalized now. No, this is unnormalized. Unnormalized. This is unnormalized, so we have an auto C action. Otherwise, we don't have such an action. It's unnormalized induction. We also need the auto C action on Archimedean cohomology. Recall we have a coefficient system. This is an equivalent bundle of this group. Now let pi I be a family of smooth admissible automorphic representations. The representation may or may not be irreducible. They are given, suppose we are given a decomposition. Each representation, automorphic representation, is decomposed in infinite part and the finite part. And we also assume this finite part carries an auto C action. We have such an equivalent bundle. And we also assume that these relatively algebraic cohomology, we know under certain condition on this phi and these automorphic representations, there is a natural map from this cohomology space to this space. Okay? And we assume this space is non-zero and this map is embedding. Okay? Here G is the algebra of this complex group. Then, under this assumption, there exists at most one action of this auto C on this bundle of all Archimedean cohomologies. We put all Archimedean cohomologies together. This is a bundle over this index set I. Okay. We want an auto C action on this bundle so that this structure map to this I is auto C equivalent. There exists at most one such action such that we require two conditions. The first one is this space is an EI rational form inside this space. Okay. So this also means the Galois action is continuous in some sense. And the other one is this map. We have a natural map of fiber product of I of this bundle with this bundle to this bundle of all static homologies. Fix I, we have the tensor of product of this cohomology space with this non-Archimedean representation goes to this cohomology. Okay. We always have such a map. We require this map is auto C equivalent. With these two conditions, such an action exists. If it exists, then it's unique. If such an action exists, we say that the rationality hypothesis holds. This is the first step to study rationality of L function through this modular symbol method. This example is due to Clausius for cuspidal cohomology. Let G be JN, and let this I to be the set of all regular algebraic irreducible cuspidal automorphic representation of this GA. And use what model we can decompose this representation, pi is just pi, to Archimedean component and non-Archimedean component. And also, as I mentioned, this example of Harder and Menkoff, we have an action of auto C on this bundle. Then, in cuspidal cohomology, we know this cohomology space this cohomology space is non-zero. Yeah, this Fi is just a coefficient system, also weight of this pi I. Then this space is non-zero, and the natural map from this space to this beta cohomology space is injective. This is due to Clausius. Is this injectivity due to?
I'm sorry.
This injectivity is proved by who? This D should be some D, not every integer D, of course. Yeah, in some interval. Right hand side? Yeah, this is compact supported. This is compact supported cohomology. Yeah.
You don't want
Sorry. No, but for yeah, this representation is almost irreducible. The injectivity is more or less the same as non-zero. Then the rationality hypothesis holds. So we have a rational structure on this bundle. This is due to causation. This fish maybe shouldn't be.
The second line is fine.
Yeah.
It's okay.
Yes. Problem is injectivity. Why this map is zero? If this is zero, then it go to arbitrary support cohomology is also zero. This is not correct. The map from this cohomology space to the beta cohomology of arbitrary support condition. We know this is non-zero or it's injective. This induces this map is also injective. No problem. We an example of Eisenstein cohomology. We prove this by following an idea of hardware. The P is before the stabilizer of a hyperplane in Kn, which has a map to J1. And let this I to be a set of all algebraic characters, I equals eta, such that this unnormalized joint principal series representation is regular. Regular means that the median component has regular infinitesimal character. Median component is admissible representation which has infinitesimal character. We assume this infinitesimal character is regular, so that this representation contributes to cohomology. Then we have an action of auto C on this bundle. These are realized as induced representation. This is just sigma linear map acting on function on GA. Yeah, I'm going to talk about the rationality hypothesis. Now we suppose K is of CM type, means K contains a CM field. If K contains a CM field, then we say that the number field K is of CM type. And assume D is this number, which is the minimal degree of cohomology for this representation. Under this assumption, we know this the joint principal series is irreducible, and the Eisenstein series is holomorphic in the holomorphic at is equal to 0, maybe. So, the Eisenstein series yields an embedding of this the joint principal series to the space of, sorry, this is not a cusp, to the space of automorphic forms. no task here. Here, infinite means the space of smooth automorphic forms. I always work on representations, not GK module, modular representation. Then we show that in this degree D, this map is injective. Here phi is the support condition are all closed set, okay? Arbitrary support. And we know that this map is injective and this space is 0. And we also prove that in this case, the rationality hypothesis holds. So we get an exchange of auto C on this bundle of median cohomologies. This need a proof. We prove this by studying some the constant term and the rationality of certain intervening operators. So we can talk about module symbols and the Archimedean module symbols. Recall we have an index set I, which carries a continuous action of auto C, and we have a family of automorphic representations, and we suppose each of these automorphic representations decomposed is infinite part and the finite part. And we are also given a coefficient system, the equivalent bundle of this group. And we also assume that we are the union of all these non-Kimmy parts carries an action of auto C. These conditions I have mentioned. And we also assume that this cohomology space is non-zero and embeds to this beta cohomology space. Okay. Now let H be an algebraic subgroup. We assume that the intersection of A with this H restricted to Q is finite. Under this condition, we can define this Perry integral when this integral converges, at least. Okay. Yeah, MH means some one-dimensional space of Haar measures. This is right invariant Haar measures on HA. And this space further decomposed is M infinity and M infinite. If this is a space of right invariant Haar measure on the Archimedean group, this is the space of Haar measure on non-Archimedean group. Okay. No, this is one-dimensional space, not that important. In some cases, we can unfolding the Perry integral to get a factorization of this Perry integral. This is called ZI. This Perry can be written as a product of median local pairs. This is usually defined by certain normalized zeta integral. And we also have normalized zeta integral at non-Archimedean place. And this one is usually some value of L function. Value of complete L function. To study modular symbol, we also need invariant function of the coefficient system. So we need an equivalent section of this bundle. So this means a map J from I from this bundle. We assume this map is equivalent under this group. This means for each I, we need to fix a vector lambda I in Fi that is invariant in this group H. Okay. And also, the choice of this invariant vector should be compatible with respect to auto-selection. Okay. We need such a family. For example, we consider the case when G is quite split and H is spherical. In this case, we can take an element W, a rational point W in G of K, such that BWH is open in G. Okay. When H is spherical, we can always take such an element W. Okay. And then we let Fi to be the vector in Fi that is fixed by this group H, and with this property. So if this space is non-zero, when we require the value of lambda I at W is 1, otherwise it's just 0. Okay? If we define lambda I by this formula, then this guy is is equivalent under this group action. This is a compatible family of the branching of the white system, of the coefficient system. We need such a family. Now, use this family, we can define the module symbol. This is the map from this cohomology tensor with some one-dimensional space involving high measures and orientations. Okay. We need the orientation also. First, we have a map, an embedding from this space to this beta cohomology. Okay. Then we take restriction of cohomology. We assume phi has certain property so that it induce map from this to complex spot. Sorry, this star should be D. Sorry, this star should be D. Okay. Then we use restriction of cohomology and also the function of lambda I. Lambda I is the element in Fi, so it is identified with a linear function on Fi dual. Right? We have an H invariant functional on this white space. And together, this induces a map from this cohomology space to this. Okay? This cohomology space. And for this cohomology space, with coefficient system in C, we have an integration. This is just pairing with the fundamental class. Yeah, D, yeah. In this case, we assume D equals this dimension. Style D, sorry, I have a typo. This style D, and the D is equal, we assume D equals the dimension of this manifold. D is the dimension of this manifold. Assume.
But it's
Style D, I have a typo, sorry. Yeah, it's style D, this is a typo.
It's not the dimension.
Yeah, style D, and the D is a dimension. Yeah, yes, thank you. And yeah, here this space in order to have pairing with the fundamental class, we need an orientation of the manifold as well as a hard measure of the non-Archimedean group. We need a hard measure of the non-Archimedean group and an orientation. With these two, we have such a map. So this is called the module symbol. And then this module symbol has a factorization to this. We know this space has a factorization. Okay? Is the tensor product of the non-Archimedean group representation in the Archimedean cohomology space. And this module symbol has a factorization of this functional on the non-Archimedean group representation, as well as this guy is called, which is called the Archimedean module symbol. This is the name of the talk. So we consider the cohomology of this Archimedean group, okay, and take a tensor with the orientation. Then we can have first we can take a restriction of cohomology to the smaller group H. Okay. Then we can also fix through this OH orientation as a tensor product of this measure space and this wedge. Okay. And use this measure, we can we have a functional on this space. This is the normal zeta integral, and also we have lambda I, which is weight, which is a function on this space. Then we get a map from this guy to this cohomology. And we put this this wedge D. And this space is identified with C. Then we have a linear function on this cohomology space. This is called the Archimedean module symbol. So the global module symbol is, in some cases, we have a factorization of this global module symbol, the tensor product of Archimedean module symbol with this non-Archimedean zeta integral. Then the ratio is this L value. So we study the arithmetic property or periodic interpolation by studying rationality of these three functionals: Pi, this Archimedean module symbol, and this non-Archimedean functional. Recall that this non-Archimedean functional is assumed to be non-zero. Okay? And we call the non-vanishing of this Archimedean module symbol to be the non-vanishing hypothesis at infinity. This example, this also need a proof. This is not obvious. Yeah, now we can define automorphic period. We assume the rationality hypothesis holds so that we have an auto-C action on this bundle. And we also assume the non-vanishing hypothesis at infinity also hold. Then we can always choose auto-C equivalent section of this. This is a map from I to this bundle of rational cohomologies, Archimedean cohomologies, such that the Archimedean module symbol, the value of Archimedean module symbol at this omega I is non-zero. This can always be done. This is just a choice for each I. This is a choice of cohomology class, rational cohomology class. Now we can define the Archimedean periods just to be the inverse of all these numbers. Okay? This is the element in C cross to the power I. Okay? We can ask, is this family uniquely defined? I remark, the following are equivalent to each other. The first one is we can consider kernel of this Archimedean module symbol, okay, this guy. We put the union of all these kernels. This is a sub-bundle. The kernel is auto-C stable. Okay. This is one condition. And the other one is omega infinity uniquely defined inside this space. Okay, E cross is just inverse limit of EI. Here we consider I as a category. Morphisms are just, this is actually a good point. Morphisms are given by auto-C elements, which maps I to J. Then we can take inverse limit. This is isomorphic to this guy. And the other one is that this map is auto-C equivalent. In many cases, we can verify that these three conditions are satisfied, so that this, in particular, this Archimedean periods is uniquely defined. We can, similarly, in the non-Archimedean setting, we can choose an auto-C equivalent section, okay, that these normal zeta integral are vanishing on each ui. Then we define, similarly, we define the family to be the non-Archimedean periods. Similarly, we have equivalence of these three. The union of this kernel is auto-C stable, and this non-Archimedean periods is uniquely defined, and the map is auto-C equivalent. Now, in this general setup, we know this map is auto-C equivalent. This is the reciprocity law. This is reciprocity law. In particular, this quotient belongs to EI, the rational. We call the product of these two guys the automorphic pairs. This is similar to the Deligne conjecture. The special value divides this automorphic pair is rational. So the problem is to, in some examples, we want to describe these Archimedean pairs in the non-Archimedean pairs as explicitly as possible. Often, this one is much harder to calculate. Archimedean one is much harder. We also call this number, Z number is, so we consider three examples. First one is example of Rankin-Selberg function for Zn cross Zn minus 1. In this case, we let G be the product of these three groups. Okay. We also add J1, and let H be the subgroup of, let H be Jn minus 1 to be viewed as a subgroup of G, where this map. We said that an irreducible algebraic representation F of this complex group to be balanced if there is a H invariant vector in F. Now we consider let I be the set of all regular algebraic cuspidal automorphic representations of this group G with balanced coefficient system. Then we have each I is representation. So this representation, we denote this by pi I. Okay. In Euler model, we have such a decomposition, and also we have such an extreme of auto-C on Z. And by Rankin-Selberg theory, we have a factorization of this period integral as a product of this low value, and this median zeta integral and the non-median zeta integral. We let the K infinite prime to be the standard maximum complex group, and let D be the dimension of this manifold. It agrees with the minimal cohomology degree of the cohomology of these representation pi infinite. We have cuspidal cohomology, which embed this to phi. Yeah, phi is, since I'm talking about the cuspidal representation, this phi can be complex spot. And we know the rationality hypothesis holds, so that all these the rational cohomology classes has a rational structure. Median cohomology space is a rational structure. Then we know, is conjectured by Deligne and Meiser, the non-vanishing hypothesis at infinity holds in this case. And in this case, the Archimedean period is uniquely defined, and we can calculate it explicitly. This number is certain. I call this vector period. This is number only depends on pi n minus 1 and some kind of sign of this. And with certain express number given by the weights of these representations. Okay. And in the non-Archimedean case, harder for Gel2 maybe Markov prove that these non-Archimedean pairs is uniquely defined, and actually this pi should be I. Because if I equals, it's just a product of Gauss sum. Pi n minus 1, this is the central character of the representation pi n minus 1. This is just a product of Gauss sum. Here is explanation of this constant omega mu nu cap. Yeah, mu nu cap is the highest weight of the coefficient system. Yeah. Then mu is a family of integers. Mu is also a family of integers, so it's cap. And we can calculate this explicitly. And this guy, for every sign, that means a quadratic character of the Archimedean group. Okay. For every epsilon, we have a non-zero complex number. This is called the vector period of this representation. Okay. This is independent. This family is independent of chi. This is some kind of sign determined by chi. We know that this is a definition of Gauss sum. In particular, we know that this special value, after dividing by this vector period, this is a power of square root of minus 1. Power of square root of minus 1. These are Gauss sum. After dividing these guys, this is a rational number. This is an algebraic number, at least. There was a lot of work on this theorem. In the case of Gel2, Mueller, and also Hid here. But for general N, there are also a lot of work. We can also consider the case of Rankin-Selberg function for Barbie can also work on this. You calculate this one by assuming the cohomological test vector, existence of cohomological test vector. We also call this number the modifying factor at infinity for periodic L function. Since for construction of periodic L function, we need to modify the factor both at infinity and at p. This is also the number we are used to modify the L function at infinity. This is called modifying factor at infinity. This is Rankin-Selberg for Jn cross Jn. In this case, we have to assume K is of CM type. Then we consider the product of 3 Jn over divided with J1 in the center diagonally embedded. The H is Jn over J1 diagonal embedding, and let I be the set of all regular algebraic cuspidal automorphic representation of Jn cross J1. This is K. We assume that I eta. Here eta is just the product of these three guys. This means the central character of sigma. Okay? Product of these three guys, this eta. We assume that I eta is regular, and this representation has a balanced coefficient system. Okay? We consider set I of all these representations. Eta is the Deligne principal series as before. Then use Eisenstein series, we can realize pi I is a space of automorphic representations. And use the Whittaker model in the example 5 before, we can factorize the representation pi I, and we have an auto-selection on these non-Archimedean representations. And we have Rankin-Selberg theory. So this zeta integral can be unfolded to the product of the local with this L function. This is a little bit different from the Rankin-Selberg L function, dividing by the special value of Hick L function. Yeah, then we can, similarly, we can, all these things, we have rationality hypothesis, and we can prove the non-vanishing hypothesis also holds, and we can also describe these numbers, Archimedean pairs. This is similar. This is a Whittaker pair for sigma times sigma prime, and some concrete number. And in this case, non-Archimedean pairs can also calculate the Gauss sum. Here is explanation of this guy. This is a little bit more complicated than GLN cross GLN means one case. Anyway, it's a power of square root of minus 1. In particular, we have such a rationality. The case of n equal to 2, this is due to hidden. For general n, Granny has studied this problem. This with Miyazaki, they have calculated some explicit Rankin-Selberg integrals of principal series representation related to this problem. Final example is about a Hick-L function. Now we assume K is the same field, and the K prime is a field extension. Then we consider the group G, which is this is G prime. We consider K prime as a vector space of a K. Then we can have a general linear group. Okay? For the G prime, this is a general linear group of a K. And then we consider G prime product with this G1 restricted to K. And then GL1, the group GL1 diagonally embedded to this product. We consider the quotient. Okay? This is G. And then let H be this is torus. Torus mod GL1. This is a subgroup of G by diagonal embedding. Okay? You know this torus is a subgroup of G prime, naturally. Then we let I be the set of all critical algebraic characters. And we can consider, given I, we can consider this representation of G. This is a normal induction. This cancel with this K prime. This K prime is a representation of this guy. And this guy is a representation of G prime. Okay? Where P is the stabilizer of this K perpendicular. Here K prime, we use transform. We have an orthogonal decomposition of K prime is K and its perpendicular space, orthogonal space. We have the representation pi I. Then we use Eisenstein Series to realize this pi as an automorphic representation. And as before, we have a decomposition and here's auto selection on these non-Archimedean group representations. And by tight thesis, we have a factorization of this Taylor integral. This is normalized Archimedean zeta integral. This is non-Archimedean zeta integral. This is a choice of how to choose the K infinite. Then we have all this stuff, and the non-vanishing hypothesis holds, and this Archimedean periods is uniquely defined, and we can calculate these Archimedean periods in terms of the weight of K. This cup is the weight of character K. Yes, K. And this is also uniquely defined, and we can choose them to be one. Here is the definition of the cup. This is just more or less a discriminant. This is discriminant, and this is relative, some kind of relative discriminant. Okay. And in particular, we can show that the divides the quotient of this special value with this kind of code. This K is just a restriction of K prime to a character for K. Small group. This quotient is rational. This as a consequence, this proves the Deligne conjecture for character of CM type fields. For CM fields, this is proved by Blasius a long time ago. And the recently for CM type fields, this is proved by use some method of algebraic geometry. 1918. Proofness proof use method of algebraic geometry, I think, like Don Blasius proof in same field case. This statement reduce the Deligne conjecture for Hecke character to the case of CM field, and the proof is quite short. And this, I think, this is such a result was claimed by Harder and Schiappardi in 1980s. They claim such a theorem, but details never get. Thank you. That's all.